Hey guys, welcome to chapter 13. In chapter 13, we're going to talk about solutions. And then the end of the chapter, we're going to talk about colligative properties, which is what our lab will be about. So, chapter 13, we're going to take it back to talking about solutions. So, in the first slide, I want to just review what a solution is and then talk about the different parts of a solution, because I'm going to be using those words a lot this chapter. So remember that a solution is defined as a homogeneous or homogeneous mixture of two or more substances. So that homogeneous or homogeneous means uniform throughout, or it looks the same. You can't tell where one thing starts or stops. It looks the same from top to bottom. So the classic example of that would be coffee with creamer. So when you look at a cup of coffee with cream in it, it just looks like a tan substance. You can't tell where one thing starts or stops. There's two different types of substances that are present in a solution. So the solvent, it would be the substance in greatest proportion. The solute would be all the other substances in lesser proportion. So if we stick with our coffee example, the solvent would be, we'll say the coffee, for example. And then the solutes would be the sugar, the cream, the caffeine, all the other different particles that you find in there. I'm going to be using the words solvent and solute pretty fluently in this chapter, so it's important that you guys start to commit those to memory. So a solution can be a combination of a liquid, a solid, or a gas, and really any combination of that. Typically, when we think about solutions, we think about a water-based solution, so something like salt water, where we have our water as the solvent. Salt would be our solute. But this slide is just to address that we can have different types of solutions. So for example, the air that we breathe is a gas-gas solution. You can have a solid liquid solution, so that would be the salt and water. And another fun one to think about is like the gas and the liquid. So if you've ever had club soda or any like sparkling drink, the CO2 would be the gas and the water would be the solvent. So lots of different types of solutions to talk about. Again, we're probably going to stick with that water-based solution for the most part in this chapter because that's the easiest for us to understand. The other thing that comes to mind when we talk about solutions and putting something in solution is this idea of solubility. So solubility is the amount of a substance, so amount of a solute, that will dissolve in a given amount of solvent. So we all know that salt dissolves in water, but there's a limit to that, how much salt we can put in before the water can't hold any more of that salt. So that limit is the solubility. So one substance, solute, dissolves in another substance, solvent, it's said to be soluble. So we put salt in water, we give it a little stir, the salt disappears, soluble. Sticking with the theme of not all solutions are water-based, so we can have something like bromine is soluble in methylene chloride. Nothing that you're going to have to memorize there, just showing you that we can have other types of solutions outside of this water-based solution. When one substance does not dissolve in another, it's said to be insoluble. So we went through a whole list or host of these in Gen Chem 1, where we determined if something was soluble or insoluble. Another example would be oil and water. So when you put oil in water, give it a little shake, the two never mix. They always stay separated. So that would be an example of insoluble in water. Solubility, there's a lot of factors that determine solubility, whether something's soluble or not. It depends on things like intermolecular forces, so we'll get to that a little bit later. But it also depends on something called entropy. So nature just has this tendency to mix. So if we put two things next to each other, those two things don't inherently stay apart and separate. Typically, if we put two things together and they have the ability to mix, they will mix together. And that is a phenomenon called entropy. So certainly nature's tendency to mix things does in fact assist in solubility. So entropy is the measure of dispersion or measure of randomness in a sample. We are just simply introducing entropy in this chapter. We'll talk much more about it in a later chapter. So here we see there's a persuasive tendency for energy to spread out or energy to disperse. So given the opportunity, it's not going to all stay in one place. If given the opportunity to spread out into a bigger space, it is going to do that. That is a little bit more stable for it. Here we see an example of this, just a really kind of silly, simplistic example. But here we've got neon gas and argon gas, and as long as they're separated by this divider, we got neon on the left, argon on the right. But the second that we take that divider away, argon isn't going to stay over here, neon stay over here. The tendency is going to be for those two to mix together in that container. So that tendency to mix together or randomize is called entropy. Another example of this idea of entropy or nature's tendency to mix is thermal energy. So if you've got a if you've got a piece of metal and you stick one end into the fire, that that heat will eventually creep up the metal and reach your hand. So it's the reason why thermal energy flows from the hot end of a rod to a cold one. Again, it's dispersing or spreading out or randomizing that heat. It's not all going to stay at the tip of that rod. So just another example of entropy. So that's just a quick introduction to entropy. We'll talk about the ins and outs and calculations associated with it in the coming chapters. So how does a solution form? So here we're going to introduce the intermolecular piece of solubility. So a solution forms when a solvent pulls solute particles apart and surrounds or solvates them. So here we see three different snapshots of a solution forming. So here's our classic ionic compound, sodium chloride. So the chlorine would be the green, sodium is the purple. When you drop a little pellet of salt into water, what happens is the solvent, which is our water, pulls the solute particles apart. So water wiggles in between these particles and plucks them to different areas inside of this container. Then those particles are going to be surrounded by the water molecules. So here we see our negatively charged chlorine ion surrounded by our water with the hydrogen sticking in. And here we see our positively charged sodium ion surrounded by water with the oxygen, which has the partial negative, so the oxygen facing in. So this is the process of those water molecules breaking up the solutes and surrounding them. And here we see a completely dissolved situation where all of the ions are separated. So the intermolecular forces between the solute and solvent particles must be strong enough to compete between the solute and the solvent. So what we're going to lay now what we're going to lay out in just a second is kind of a three-step process. So solute particles interact with solute particles, and solvent particles interact with solvent particles. And then we also have the solute-solvent interacting. So there's kind of three different situations that are going on that are at play, and we'll break each of those down in just a moment. But before we can dive into the interactions, we have to remind ourselves what intermolecular forces are, what intermolecular forces might be at play. So again, here are our four intermolecular forces. We've got our London dispersion. So London dispersion is the weakest. It's felt by all molecules. If it's a non-polar molecule, then this is the only one that it feels. So this is that temporary or fleeting attraction, that momentary dipole that causes these to stick together for a second and then release. So not a pole or not a permanent pole, but just a temporary one. Then we've got our dipole-dipole. So dipole-dipole is going to be an interaction between two polar molecules. So we've got a polar molecule acetone here with a partial negative on the oxygen, attracted to a polar chloroform molecule here, and there's a partial positive right here. So partial negative, partial positive, those two are interacting with one another. So dipole-dipole. Then we've got kind of the extreme case of dipole-dipole. We've got our hydrogen bond. So again, it's still two polar molecules that are being attracted to one another, but specifically there's a hydrogen, oxygen, hydrogen, nitrogen, hydrogen, fluorine bond. So it's just a very elite group of dipole-dipoles, if you will. So here again, we see this OH sticking out from ethanol. So partial positive on the hydrogen is attracted to this oxygen on the water. So again, an OH puts us into that elite hydrogen bonding. So hydrogen attracted to an oxygen. And then lastly, something we will need to consider is this idea of the ion dipole. So the ion dipole interaction would be an ion, so something with a complete charge, a +1, +2, -1, -2, something like that. So that would be the ion portion of this, and then a polar molecule being attracted to that ion. So again, we've got our polar water molecule here being attracted to our positively charged sodium. And again, we see that the partial negative on our oxygen causes all of these to face oxygen in towards that positive charge. Okay, so that's the ion dipole. So energy changes, which we'll talk about in a little while, in the formation of solutions is involved in the differences in the attractive forces between the particles. So are we trying to overcome dispersion to create a hydrogen bond? Are we trying to overcome hydrogen bond to create dispersion? So what types of intermolecular forces are happening between solutes and solvents that will dictate or determine whether or not something is soluble, something actually dissolves in solution, or would it rather just interact with itself and be insoluble, not dissolve in solution? So there's three places that we have to think about intermolecular forces, three different places that we have to think about interactions. So let's say that this solution right here is our classic example of salt dissolved in water, okay? So first thing that we have to consider is the idea that water is attracted to itself, right? So solvent-solvent interactions. So solvent-solvent interactions, if we're dealing with water, certainly water is attracted to other particles of water via hydrogen bond, right? Then we have to think about the solute molecules. So solute is attracted to solute in some form or fashion. If we're talking about salt in this case, salt is attracted to itself via ionic bonding, right? Positively charged sodium attracted to negatively charged chlorine. So the solute-solute interaction here would be an ionic bond that we would have to get rid of. Then we have the solvent-solute interaction. So water and sodium, or water and chlorine, will certainly be attracted to one another. In this case, that would be like an ion dipole interaction, okay? So we have to consider the solvent interacting with itself, the solute interacting with itself, and then when we mix the two together, how do they interact, or do they interact with one another, okay? This process does not happen as a step 1, step 2, step 3 process. I'm going to break it down that way. Your textbook breaks it down that way, just because it gives us a logical path through these problems. But this certainly happens kind of all at the same time, in and out with one another, weaves in and out of these steps. But we'll break it down into step 1, step 2, step 3, so that'll give us a really good, clear path to take when we logically think through these, when we critically think through them. So step 1 in the solution process is going to be, excuse me, separating the solute particles. So in this case, we're going to take maybe sodium chloride, which is this crystal structure, and we're going to pull that crystal structure apart so that the water molecules can wiggle in there and interact with them. So we've got to separate the solute particle from itself so somebody else can interact with it. This, remember, is denotes change in enthalpy, which is the change in energy. So we as chemists study energy, typically in the form of heat. And when we're doing this in a open system, we don't say heat, we say enthalpy. So this delta H, remember, is just how is the energy changing. So the process of pulling these solute particles away, the enthalpy change or the energy change is going to be greater than 0. It's going to cost us some money for this to happen. We're going to have to put energy into the system in order to pull those particles apart. That really shouldn't be too groundbreaking. If they're stable as a ionic compound, of course we're going to have to force it or put energy into breaking those particles apart. Okay? The amount of energy that we have to put in there is something called lattice energy. So the amount of energy that is released during the formation of a solid is how lattice energy is defined. And in order to break it apart, basically what we're doing is we're overcoming lattice energy. So we're going to have to put in that exact amount of energy to break it back apart. Okay. So that's what we're overcoming here to break it apart. So this would be an endothermic process. We have to put energy into it. We have to pay a little bit up front. Step 2 is we got to separate the solvent. So same thing, solvent and solvent are interacting with one another very close together. So certainly we're going to have to break those two particles apart in order for the ionic compound to come in and interact with it. So again, this is going to be an endothermic process. We're going to have to put energy into the system in order to break those particles apart. They're attracted to one another, and we're going to have to pull them apart so that they're not so close. So separating the solvent particles from each other to make room for solute. Endothermic, we have to put energy into the system. Okay. So if I have to put energy into the system to break apart solute, if I have to put energy into the system to break apart solvent, why in the world would anything form a solution if we have to pay so much money up front? Well, step 3 is where we get our return on investment. So step 3 is when we mix the broken up solute particles with the broken up solvent particles. So when these two come together, if it is a soluble compound, when these two come together, they will mix together, and the mixing together is going to give us a huge release in energy. So mixing these two particles together is going to form some sort of stable situation. That's everything we do in chemistry, is to gain stability, to lower the energy. So when we mix these two things together, they become more stable. We get a huge amount of energy released. So that would be an exothermic process. Energy is given off during this process. So the change in enthalpy, or the change in energy, is less than 0. So it's going to be a negative number. Energy is exiting the system. Okay. So is something going to form a solution or not? Well, we've got 3 things to consider now. We've got to consider the energy that we put in to break apart the solute. We've got to consider the energy we put in to break apart the solvent. And then we got to consider the energy that we get out. So essentially, what we're going to see is an equation that looks a little bit like this, or a thought process that looks a little bit like this. We're going to have the change in enthalpy of breaking apart the solute plus the change in enthalpy for breaking apart the solvent. And we're going to subtract that from the change in enthalpy we get from mixing the two together. Excuse me, we're going to add that to that. Okay. So the amount of energy to break apart, the amount of energy to break apart, and then the amount of energy that we get back. And then we're going to compare that to the number 0. So if it's bigger than 0, something's going to happen. If it's less than 0, something's going to happen. Or if it's exactly at 0, what's going to happen there? So this is going to be the math process that we have to think through as we're working these problems. Okay. So here is the result of that. So if the solvent-solute interactions is really big, and the solvent-solute interactions is a little smaller, then a solution is generally going to form. Okay? So this is actually going to be a number that's less than, that's not less than, less than 0. Okay? So this would be a number that would be an exothermic number. Okay? It would be something where energy is released, and a solution generally forms in this situation. Okay? If the solvent-solute interactions are, we'll say, moderate, and the solvent-solvent and solute-solute interactions are moderate, a solution is generally going to form. So if those are about the same, if we're roughly equal to 0, then a solution, again, will generally form. Okay. If the solvent-solute interactions are low, so not a lot of energy released, and the solvent-solute interactions are very strong, so they like interacting with themselves, a solution may or may not form. There's other things that we certainly have to consider. But pretty much for this chapter, we'll say that no solution forms. And this would be a scenario where enthalpy would be greater than 0. So it'd be an endothermic process. We have to put energy into it. And typically a scenario where we have to put energy into it is not going to happen. Okay, we don't like to force things to happen in chemistry. Okay. And then the formal word that we use here is if two substances are soluble at all proportions, we say they're miscible. So that would be a case where if this number was really, really big and this number was teeny tiny little, it doesn't matter how much we put in, it will always dissolve. That's what we say would be miscible. Okay. All right, so this gets us to one of these really major concepts in chemistry of like dissolves like. Now we have the skill set, the foundation to understand this. So what like dissolves like means is if it is two polar compounds. So if it's a dipole-dipole, hydrogen bond, ion dipole, so if it's two polar compounds, they typically will dissolve with one another. If it is two non-polar compounds, so this will see a lot of organic compounds that are a bunch of C's attached to each other with a bunch of H's coming off, okay? So all of these bonds are non-polar bonds. And if I mix that with something else that's non-polar, these two will also be miscible with one another, will dissolve with one another. So when we say like dissolves like, polar dissolves polar, non-polar dissolves nonpolar. Okay. And so here we just see some common solvents, not anything you're going to need to memorize. It might be a good table to refer back to with some of your homework questions. It's certainly something that I'll help you with on an exam. So water, we know, is a polar molecule. Acetone is also a polar molecule, so it's got this oxygen sticking up. So this bond right here is a polar bond. So we got a partial negative up here, partial positive down here. Methanol has that OH sticking off the side, so that would be a hydrogen bond. And same thing with ethanol, it's got that OH, so that would be another example of a hydrogen bond. So any of these compounds, if they were mixed together, they certainly would be soluble. So I can mix water and ethanol, your alcoholic drinks. Those two are certainly soluble. I could pick mix methanol and acetone, and those two would be soluble. Over here, we've got our non-polar solvents. So here we see a bunch of carbons and hydrogens attached to one another. So those would be certainly a non-polar. Again, another bunch of carbons and hydrogens. And here we see carbon tetrachloride looks something like this. So this is where it would pull equal and opposite. And so there would be no dipole moment. So any of these substances, if we mix them together, so I can mix hexane with carbon tetrachloride, and we would have a compound that is soluble. Those two would mix together. If I tried to mix anything over this middle divide, what we would find is an insoluble. So if I put water and hexane together, what would happen is you would see something like this in the beaker, where your water would be down here, and then you would have the hexane up here. So there'd be a line where you would see they certainly are not mixing. They're not dissolving with one another. So you'd see two separate layers, much like you do with oil and vinegar in a salad dressing. So this like dissolves like is a concept that you'll see a lot in chemistry. Certainly if you move on to organic chemistry, this like dissolves like is something that we use in a laboratory to purify substances. So it's certainly something you're going to see again. We like to introduce it here in Gen Chem. Another example of like dissolves like would be if we were talking about vitamins. So this gives us a pretty tangible example of trying to understand this idea of like dissolves like. So vitamins are categorized as either fat-soluble vitamins or water-soluble vitamins. Water-soluble vitamins dissolve in body fluids and are easily eliminated through the urine. So there's no danger of overconsumption. Fat-soluble vitamins accumulate in the body's fat deposits. So examine the structure of each of the vitamins and classify it as either fat-soluble or water-soluble. So I'll tell you right now that fat is nonpolar. Okay, so fat is a nonpolar substance. So if we're thinking like dissolves like, a fat-soluble vitamin would be less polar or nonpolar. Okay, water, we know, is a polar substance. Not popar, polar is a polar substance. So if it's a water-soluble vitamin, that means it is a polar molecule. Okay, so let's look at our two vitamins, vitamin C and vitamin K. If I look at vitamin C, I see lots and lots of opportunities for hydrogen bonding. So anytime you see an OH sticking out like this, that's an opportunity for hydrogen bonding to take place. Okay, so oxygen bound to a hydrogen, there's certainly going to be a dipole moment there, and the dipole moment is an extreme dipole moment. We give it its own category. And then I see bonds like this, which are also dipole moments. So carbon and oxygen bonds tend to be fairly polar bonds as well. So I see lots and lots of polar bonds over here. So I'm thinking that this one is a pretty polar molecule. Okay. Let's go over here to vitamin K. What do we see? I see carbons and hydrogens and carbons and hydrogens and carbons and carbons and carbons. And we know this carbon-hydrogen bond is a nonpolar bond. So far, all of these that I've traced are nonpolar. I do see two opportunities here. So I do see a carbon-oxygen and a carbon-oxygen. So there is a little bit of polarity there. But if you look at the size of this molecule and these two little areas, this is a pretty non-polar molecule. Okay. So looking at these two, what I see is a very polar vitamin C, a relatively non-polar vitamin K. So I would say that this one is probably fat soluble and this one is probably water soluble. And that is the case. So now let's think about consuming vitamins, okay? So one of the things that some people recommend is if you're feeling sick or you think you have been exposed to somebody with a cold or whatever, is to start taking mega doses of vitamin C. So you can take a mega dose of vitamin C and it's really not going to affect you. Your body's going to use the vitamin C that it needs and then it's going to excrete the rest of it in your urine. So that vitamin C being water soluble is going to dissolve in your body fluids and it'll be eliminated in your urine. So kind of one of the running jokes is Americans have the most expensive pee in the world. And that's because we consume a lot of vitamins that if our body doesn't need them or doesn't use them, we just excrete them in our urine. Vitamin K, on the other hand, is something that you can only get with a prescription. So vitamin K is dosed and the dosage is monitored, is very closely monitored. If you were to take a mega dose of vitamin K, what would happen is it would store up in the fat within your body, so in your body's fat deposits, and it would have no way to eliminate it. So too much vitamin K in your system would start to shut things down. It could be very dangerous. So vitamin K is one of those things that's prescription only and monitored very closely when it's given. So fat soluble versus water soluble. So that's going to end this first video here. So just the first introduction into solubility, really breaking down the process of solubility and what's going on at the molecular level. What we're going to do in the next video is break down this idea of an endo and exothermic process a little bit more, and then we're going to talk about ways that we can affect solubility. So how can we increase it or decrease it? I hope you guys found this helpful.